All right. Thank you so much all for coming to KCITY's webinar. Today's presentation is by Professor Charalampos Papamanthou, but he goes by Babis Papamanthou. So you can call him as Babis. So Professor Papamanthou graduated from Brown University with a PhD and postdoc at UC Berkeley, and he's currently directing a co-director of Yale Applied Cryptography Laboratory. And he also chief scientist of a startup company called Lagrange Labs. I was just looking at his CV. He has such a long list of awards, so I'm not going to read all these things, but there are a few interesting awards like Test of Time Award. That sounds so fancy. And he's got award from JP Morgan Faculty Research Award, Google Faculty Research Award, Yahoo Faculty Engineer, Engagement Award. Your award sounds so much fancier than any award that we have, Babis. Congratulations.
It's just the field that I'm working on.
Right. Well, I was particularly interested in presenting and introducing Babis to Korean companies because I think he's addressing the question that everyone is asking these days when using AI. Is AI giving me the right answer? What about security of the information? Is it trustworthy? Is it transparent? These are all the questions that we all have. That means it has a huge market opportunity as we advance in AI in modern society. So I am extremely pleased to invite Babis to this webinar. And I actually myself really want to learn more about his research. Hey, Babis, here you go. And maybe 40, 50 minutes presentation. Okay.
Yeah.
Okay,
Yeah.
great. So go ahead.
Okay, great, great. Thank you, Jahong, very much. My name is Papamanthou. I'm an assistant professor of computer science at Yale. Right, so like I said, really, really grateful to be here. I appreciate Jahong's time in organizing that and helping us be exposed to such an important audience. So my area of research is cryptography and computer security. And I have worked in many areas that have to do with how to secure computation in untrusted environments. And recently, I came to realize that there are many opportunities to apply the research and the expertise that I have been gaining over the years on extremely pressing problems, security problems that have appeared due to the use of AI and due to the big AI boom, I would say, right? So I co-direct the Yale Applied Cryptography Laboratory, and this work that I will present is joint work with Hun Cho, who's a professor at the medical school, Ben Fis and Fan Zhang, who are my colleagues in the Department of Computer Science. All right. All right. Okay, good. So let me start by talking about some of the challenges in AI. We all use various LLMs and we all use ChatGPT, and all these AI systems are becoming essential to our daily life. For example, you can think about home electronics, virtual assistants. We use ChatGPT to get help with writing text, emails. Even recently, I've been noticing these systems are becoming useful in also doing research. There've been reports of mathematicians tackling various open problems in mathematics by the help of ChatGPT and LLMs. However, the observation is that as AI becomes more powerful, it faces a trust and privacy problems. And what do I mean like that? So I'm not referring to the traditional trust and privacy problems. For example, robustness is one such trust problem. For example, what happens when you perturb the input to LLM model just a little bit, and the result is completely different. Like think about a stop sign, right? I mean, there was some research when you put a stop sign and the stop sign is being read by the LLM, the car will stop. But then if you go and very carefully change a single pixel of the stop sign, right? So the LLM would this would cause to change the behavior of the LLM and the car will crash, right? So this is traditional work that has been done. Fairness, for example, it's another very important thing where basically how do you can train an LLM or a model so that you can remove any bias from it, right? And there have been important work combating these social and ethical concerns in AI. But our position at Yale and my position and my colleagues' position is that these technical solutions that deal with just improving the code of the model, the way the model is being trained, does not eliminate all concerns that are coming out of all security concerns that are coming out of the deployment of the systems, right? So I will identify what the problems are, but our goal is how we can apply uh, cryptography and security to tackle the most pressing security problems of AI models and large language models, right? And we realized I started thinking about these problems, but at the same time, I realized that at Yale we have an amazing cohort of young scientists, which I'm very proud to have as my colleagues. Here is Ben Fiss, Fan Zhang, and Hun Cho, who have been thinking around the same problems, right? So, we go together and we start talking about how we can collaborate to tackle this pressing problems using our expertise on security and cryptography, right? So we are part of this Yale Applied Cryptography Laboratory, and this is our logo. And we meet every Friday to have lunch and to discuss, about all these pressing issues. But let me get more specific about what we're concerned about. So this talk is going to touch on mainly three aspects. We're going to talk about specific trust problems in artificial intelligence, centralization problems in artificial intelligence, and privacy problems in artificial intelligence. And we propose various techniques to address these issues. Let me just say that we all participate in these three thrusts, and there's some people that are leading one thrust or the other. Me and Benefits are mostly leading the first thrust. Van Zank is leading the second thrust, and Hoon is leading the third thrust. Right. So let me start with trust problems. Okay. So we would like to be able to prove the correctness of the output that is coming out of an AI model without recomputing the model itself. Okay, so I have an input, I have an output that is claimed to be coming out of, say, ChatGPT, out of this Gemma 3 model. How do I know that this output indeed came out of this model? Well, you can tell me one way to do it is to download the model and recompute do the computation yourself again from scratch. But unfortunately, when we're talking about very constrained devices like your phone, you cannot really recompute the model, and that's why you have Amazon doing the inference for you, right? Or ChatGPT doing the inference for you. What you want to do is quickly verify that the output is the correct output corresponding to the specific input. So what we want to do is, along with the output, provide a cryptographic proof such that the cryptographic proof is a very small string, which is its size independent of the size of the computation. And by processing three things, the input, the output, and this cryptographic proof, you can verify, you can trust that the output is correct based on some hard computational assumptions, say, for example, RSA factoring, right? And we can do the same with training. Again, you get a trained model, right? How do you know that the training procedure was performed correctly, right? What you can do is you can have the entity that performed this training provide a cryptographic proof that very quickly proves to you that this is a correctly trained model, okay? So this is like one of the trust problems. We want to quickly verify results that have to do with AI models right, without having to re-execute, right? Now, there's also like an interesting privacy angle to this problem, where basically we want to prove correctness of the model output without revealing anything about the model itself. Let me give you an example. Google has come up with the most performing LLM out there, right? But due to proprietary reasons, Google does not want to make this model publicly available, but it still wants you to use the model. How will this be possible? So what Google can do is it can receive your input and it can produce a zero knowledge proof or a cryptographic proof that this output corresponds to your input with respect to that encrypted model, right? So although you don't see the model, you just see an encryption of the model, you can still verify that inputs outputs are consistent. All right. So the way I like to think about how fundamental these problems are and how pressing it is to solve those is by drawing an analogy that refers to cryptography in the internet era. When the internet was first introduced back in the 70s, nobody was thinking about security and privacy, right? And then people, start using the internet, but then they realize they have to add this additional encryption layer, an additional authentication layer on top of the internet, which, by the way, we're using right now on the Zoom connection, and you're using every day, right? So all your internet communications are secure, right? But because this came as an afterthought, it created a lot of inefficiencies, right? In how to deal with the security of the internet. So we don't want to repeat these mistakes. In my opinion, artificial intelligence, large language models are as fundamental, as groundbreaking as the internet was in the 60s and in the 70s, right? And we want to be thinking for security and privacy of these computations and of these models from the very beginning. Okay, so I believe this is a really, really important area to focus our efforts on to get this thing right from the very beginning. Okay, so let me talk a little bit about some of the applications I see of this cryptographic proof verification of AI computation. All right. So, for example, think about that a large language model can be used for very critical tasks such as a voice assisted payment, healthcare. And now what we can have is, we can have a server computing a proof that the output has been generated by the approved LLM. Okay? So, and the importance of that, why do we need that? Because even resource efficient large language models may exceed phone limits. We cannot expect to rerun an LLM on our phone to verify the output of the computation. We have limited memory, we have limited storage on our phone, and we really want to get things fast, right? So this is one application, right? Verify outputs by the approved LLM, right? The other application is verify inference with privacy. So think about the Google example I talked about before, where you commit to a model without revealing its weights, and you can prove that the inference was performed correctly using this commitment, but never seeing the whole model. Just put out a commitment, a small hash, 256 bits representing the whole model that is committing to the model, right? And then you can prove that the input output is correct. One even more amazing application of this technology is in user data privacy. So, for example, think about a mortgage application. Okay. Right now, if you are a client and you want to apply for a mortgage, typically all your private data need to be shipped to the bank, where the bank will run an ML algorithm, a model, an AI model, to decide whether you are approved for a loan or not. Okay? Clearly, this has tremendous privacy implications, right? Why should any one of us willing to share our data with the bank for that, right? What this technology can enable you to do is to have the bank provide the model to you, right? And then you can prove that my data, when fed to your model, are giving the approved condition, the approved answer, without you ever revealing your data. How are you going to do that? You're going to just commit to your data and you're going to put a cryptographic proof that this is the case. So this technology of using trust-based approaches can have tremendous applications in today's AI ecosystem. So I'd like a little bit to get a little bit more technical here, because all of this is great, but if you don't have the necessary technical background and the technical tools, you cannot build this. So the underlying technology of everything that I'm talking about is the notion of a ZK snark, which is a zero knowledge proof, right? So what is a zero knowledge proof? A zero knowledge proof is a protocol that allows you to prove that something is true without ever revealing to the world why this is true, right? So it's basically one bit of information. I give you an example. I can convince you that I know the right password to enter into my account without ever revealing the password to you. Tremendous applications. We have the technology in computer science and cryptography to do that. It's called ZK Snark. And actually, ZK Snark is the modern name of this technology. This protocol was initially invented in the 1980s as a theoretical construct. And my group and many other groups around the world have been working tirelessly to make this technology practical so that we can use it for computations that we deeply care about, such as large language models and convolutional neural networks and so on. And also in blockchain technology, which is another area that I'm very, very much interested into, right? So the idea is that a ZK snark or a zero knowledge proof allows you to verify the validity of an NP statement, a computation X, without rerunning the computation. So think about an NP statement can be a database table 1 and database table 2, a query to these databases and the result. This is an NP statement. And without rerunning this query to verify the result, you can provide a zero knowledge proof that allows you to verify the validity of X without revealing anything why this is true. Okay. Right. Okay, so our goal here is, and we have already started working on that, but we want to really take it to the next level, is to apply this technology of zero knowledge proofs and zero knowledge succinct non-interactive arguments of knowledge, ZK snarks, to the problem of machine learning and large language model. In particular, on the left-hand side, you have the server, and on the right-hand side, you have the client. So the client provides X, the input to the model, and the server makes a statement that Y is the output of the model with weights W, and here is the proof pi. Quickly, you read these four things, and the client verifies whether this is true or not. Again, no need to re-execute the computation. Extremely powerful. Okay, right. So we have started working on this problem, and one of the technical issues that we have encountered is the fact that so far we have been applying zero knowledge proofs on computations that are expressed as finite field arithmetic, but zero knowledge proof ML computations and LLM computations are floating point arithmetic computations. So this creates a huge problem for ZK snarks. In theory, you can apply the zero knowledge proofs to floating point arithmetic as well, but the overhead that is being created is too much. So this is part of our vision and our research, how to come up with better systems, with better zero knowledge proofs that are amenable to these new types of computation, floating point arithmetic, that we require to have for ML and LLMs. We have done some initial work, so let me give you like a rundown of what is our architecture. So the first thing we do when we want to prove something about an ML model is to train the ML model. as we did before. And then we export the model as an ONX file. We sample the inputs, we run some inferences to compute the distribution of the values that appear on the network. And this allows us to sort of calibrate the range of the values that of the field, the size of the field we're going to have to use in our zk snark. So this is quite important, right? Because we want to eventually know what is the maximum, what is the minimum, so we can pick the right field for our snark. All right. So here I have a very, very specific example. Now, after we have trained the model, we have the model, we have computed all the weights. For example, this is ONX file of a model we have already trained. As you can see, it has convolution, it has matrix multiplication, it has all the typical layers that appear in a convolutional neural network. And now we view this model as a graph that we're going to do some pre-processing, and we're going to generate the prover and the verifier keys. You can view the verifier key as a commitment to the model that you need to have in order to verify outputs of this model, right? Because eventually to verify something from a model, you need to have information about this model. What I'm saying here is that I'm not going to give you the whole model, but I'm just going to give you a small verifier key. Can think about it as a hash of 256 bits, right? Then the prover commits to the model weight using a polynomial commitment, and we have this different primitives that we can compute the zero knowledge proofs for. Currently, we can support matmal, gem, conv, maxpool, and relu, and etc. Right? So after we have produced these commitments for the model and we have parsed the graph, it's time to prove something, some input-output pairs, right? So how do we do it? We evaluate the model on the input, we compute the execution trace, and we compute a cryptographic proof for every step of the computation, right? In the end, after we compute the crypto, and I will show you later a very simple protocol how to do one of the steps, right? We accumulate the proofs into succinct proof of correct execution, and then we're done. Right. Uh, so the final thing is to verify. You take this proof, you take the input and the output, and you need to now decide whether it is indeed the correct output. Again, you could do that by running the whole computation yourself, but the cryptographic proof that I produced will help you do that a lot faster. Okay? So how do you do it? You just use the input and output, use the commitment key that encodes the model, you read the cryptographic proof, and you decide whether to accept or reject. The property we're having is that if the proof accepts, you have guarantee with very high probability that the input and output pair is a correct matching pair for this specific model. Okay? So let me quickly go through a working example here. This is the multi-layer perceptron. It's just a matrix multiplication followed by a ReLU function. A ReLU function just decides if you're negative, it maps to 0. If you're positive, it is this number, right? So it's exactly this computation, and we're gonna treat these two different components with different cryptographic boxes that we have studied already for a long time, and we know the soundcheck protocol was the right thing for the matmal and the lookup argument, but now we have to specialize it for the specific sort of real and floating point arithmetic that is induced by the LLM, right? So one novelty that we have here is, as you all know, the matrix vector multiplication runs in n squared time, right? So one way to verify that an output of a matrix vector multiplication is correct is to rerun the computation yourself. It turns out that you can have an easier verification algorithm where basically the prover can provide the cryptographic proof that allows the verifier to convince that this is the correct output of matrix vector multiplication just in linear time. So it's much, much faster. You don't have to do this quadratic computation to verify the input-output relation of matrix vector multiplication, and this is a key technology that we're using for our system. Okay. Of course, the underlying cryptographic approach is what we call this amazing protocol that introduced in the past is called SumCheck, where basically it allows you to verify that the sum of a fixed polynomial on the hypercube, which contains 2 to the n edges, 2 to the n points, is a specific value without having to compute every evaluation on the hypercube, which is 2 to the n time, just in n times. So we're using this as a black box. We're mapping the matrix vector multiplication, which maps to the matmal operation of a convolutional neural network, and we're able to produce cryptographic proofs that help the verifier do the work much, much faster. All right? And again, we're using other sum-check operators for convolutions, matrix multiplication, and other commonly used operations for convolutional networks and LLMs. Right. So the second part is a lookup argument, which allows you to verify the output of a nonlinear function by just storing all the possible outputs in a table. Because again, snarks work with field arithmetic. It's hard to implement nonlinear functions, so we're basically storing the outputs in a table, and we use just snarks to do the discrete computation of grabbing a value from a table and outputting for the specific argument. Right. So again, this is a very, very initial work that we have been doing on building these proofs for LLMs, and there's a lot of work to be done. Yeah, but our initial results are quite promising. So these are some performance results for a convolutional neural network with the state of the art. We're comparing with the state of the art. The setup time, basically like computing these verifier keys, we're 659 times faster. The prover is 3 times 58 faster. The verifier is 1.3 faster. And we slightly have larger proofs, but 60 megabytes is not too much, in today's internet, right? I mean, this is easy to convey, to sort of transport such a proof. Okay. So we're doing extremely well in terms of state of the art, right? But there's still like a lot of work to be done to bring these times even better, right? Again, another trial that we have is on multi-layer perceptron, where we're basically 1,000 times faster in the setup, 3 times 20 faster for prover verifiers again, and slightly larger proof, but still, within extremely reasonable. Okay. So we're super excited about this first step that we have taken, but we recognize there's a lot of things.
나중에 옮기면 안 돼요? 현재로?
Uh,
써야 되는 거네? 네네.
is there a question?
그쵸, 인쇄비에 지금 30만 원 쓸 거예요.
Okay. Okay. So we have a bunch of optimizations that we're working on. So for example, we're leverage homomorphism of FFTs to improve space and prover time. And we're also exploring other approaches for ReLU and requantization, such as replace bit composition with lookup arguments. Right. So these are key things that we're currently working on. And in the future, so this work is for convolutional neural networks, but we're actively wanting to support this for LLMs. We want to integrate with partners, and right, so we want to do a proof of training as well, and want to do a proof of ZK fine tuning. Right. So this is the first part of the work that we've been doing on the issue of trusting the results of an LLM, of a convolutional neural network. Right. There's other aspects that we've been working on. One other security problem that relates to LLMs and neural networks is the notion of centralization, right? So the main problem here we're tackling is the centralization risks of ML infrastructure, right? What happens is we have these big players, Google, OpenAI, that offer these models, this model execution in a very centralized manner, right? So we don't have multiple parties participating. So this can create problems with, privacy. We put all our data, we give all our data to ChatGPT, right? I mean, the data is power, right? And we're offloading all our data to them, right? Inference correctness, transparency, monopoly of big platforms, exploitation of user welfare. At the same time, it's there's a high cost for the provider, say for Google or ChatGPT, to run all this ML workload, right? So there is our thesis is that decentralization can benefit both the user and the provider, right? So we want to enable decentralized training and inference. And one approach is to crowdsource the computation over many participants. And this has seen growing interest actually from industry and academia. Um, Now, what are the applications of decentralized ML? We would have a new ecosystem of governed, privacy-preserving, and cost-efficient AI services, right? Uh, we will have decentralized marketplaces for ML, right? A community-controlled, transparent models, privacy-preserving inference networks, and collaborative ML training. But the most important thing, in my view, is that you could have anyone in the community participating in a way that so that the correctness can be boosted, the loss of privacy can be reduced, right? And in general, to have everyone be incentivized to participate in this ecosystem, right? So of course, to achieve the dream of decentralization of AI and ML, there's a few challenges. How we how we incentivize contribution and how to verify the correctness of contribution. So one thing, for example, is to incentivize participation. We can develop techniques that reward participation based on the improvement of the model that is achieved by the contributed computational power, right? Uh, Now, how we can enable correctness of these inferences in this decentralized fashion? Proving correctness now is becoming more difficult, right? Before, in our previous approach, we had only one server providing this cryptographic proof. But now we're going to have to come up with ideas for robust collaborative proving and use potentially more extreme and more like exotic tools from cryptography, such as proof carrying data, that allows a network of distributed provers to jointly prove a computation for a given NP statement. Uh, and another thing that we propose is to scale up this distributed verifiable model serving, right? So we would like to propose to design and develop distributed proof generation protocols to scale up the performance of a verifiable ML system. So very, very important things. I think like this second thrust of decentralization comes as a natural follow up from the first thrust, where basically, we're talking about a single server proving itself being correct. But in the real world, you need to decentralize. You need to have a distributed network of computers doing all this work, right? So it's extremely important to. So the final thing I'd like to talk about is with respect to privacy problems in artificial intelligence, right? So we talked about trust, decentralization. How about privacy? This is actually work that is being led by my esteemed colleague at the School of Medicine, Hun Cho. The work that he's doing is so important in a sense that, right now we have a lot of individuals that offer their medical data, their medical history to all these online repositories, right? So that they can get some analysis, right? So the question is how we develop the sort of secure and trustworthy AI. Now, the problem is a little bit different than the initial one because let's assume, for example, here that everybody's willing to be working correctly, to running the algorithms that they're supposed to do, right? How do we ensure that even if you do that, you don't get to see the data, the private data of the individuals that are collaborating, right? So how do we develop biomedical AI while protecting individuals behind the data? And let me give you a very, very specific example. And of course, like, I'd like to mention, like, privacy problems in AI happen all the time. There's many articles every day where, have hackers breaking into databases, storing data for training, hackers breaking databases, storing passwords. So this is a very important thing to think about how we can still get the functionality out of these powerful servers without necessarily leaking our private data. Okay. So the two goals of the project is basically secure collaborative AI training. The model here is that uh, typically right now, if you want to train a model, you don't have data coming from a single entity. You can have, for example, multiple hospitals contributing their data to train an artificial intelligence model. And the training will take place by some centralized or decentralized network of computers. Now, the question is, do these computers or must have access to all the data, right? So we want to develop protocols that allow a set of hospitals, for example, train a model without each one revealing their patients' data to one another. So we still want to get the functionality of combining our data, but not necessarily by revealing our data in its entirety to the hospital. Because remember, the weights of the model don't necessarily reveal all the information about the data that were used to train this model. So how can we build such a protocol, right? Right. And the other thing is secure and verifiable use of AI, right? Which maps back to what I said in the first thrust, where how we can verify the output of this training, right? Okay, so we can ensure that data are not leaked around, but was the training performed correctly? That's a very important aspect. And again, for this line of research, I'd like to mention that the theoretical techniques in cryptography that can be used to solve these problems are known from the 80s. It's called secure multi-party computation. It is a protocol that allows five parties to compute a function x1 on x1, x2, x3, x4, x5 without revealing anything about the individual entries, right? But the goal and the beauty of this line of research is applying this theoretical machinery to the very relevant problems of convolutional networks, large language models, right? And this transition from theory to practice can spin, can give rise to extremely interesting research problems and give rise, honestly, to many applications that I think industry, has a need for, right? I mean, this training of model on drawing data without, leaking patients' data is really natural, and we should be able to do it, right? Let me give you like a specific example now that what we can do with secure multi-party computation. So there is this notion of a disease risk, right? And there's a disease risk score for a specific disease that can be computed by having a client upload his or her genome to this computation, right? So is it possible? I don't want to reveal my genome, right? But I still want to compute this disease risk score, right? How can I encrypt my genome, send it to the hospital, send it to this provider, have the provider do the computation on the encrypted genome, and come back with a disease risk score? So this is called computing on encrypted data. And again, this is something we know how to do, but the interesting part is applying this technology to the specific problem, medical problem, or other kinds of problems that we face. Okay. Uh, and the other thing, another application I'm currently working on is just biomedical foundation models training, right? So there's biomedical models that are being used. Again, many hospitals can contribute data for the training, but every hospital needs to satisfy the privacy needs, which can be different of their patients. Okay, So how can we indeed get our job done, train this biomedical foundation model so they can be helpful to us without revealing the individual uh, patient's data? Basically, we're looking to secure and verifiable training and inference of biomedical foundation models on sensitive human data sets. I mean, I cannot tell you how excited I am about this area. And I think the opportunities are so vast. Applications in the medical sector, in the AI sector, everywhere of, bringing security into the whole picture can open up so many avenues and can, help hospitals, for example, do things much faster because the privacy, they don't have to worry about the privacy anymore. They can get things done without having to worry about privacy and without having to worry about the bureaucracy because you'll be getting the privacy guarantees from mathematical foundations of cryptography. Okay. Right. So this is basically what we have been working on. And we have some initial preliminary results, and we really hope to be exposed to people in Korea that might be interested to learn more about these things and might be having more applications that we can work on. Right. So thank you so much, and I think I will stop here.
Thank you so much, Babis. Well, there are quite a few